Hello and welcome. Tonight we'll be exploring one of the oldest mysteries our planet has ever carried: how Earth got its oceans. It is a question that seems almost too ordinary to ask. After all, water is everywhere around us. It falls quietly from the sky, gathers in rivers, stretches across vast oceans, and even flows through every living cell in your body. Because it is so familiar, it is easy to forget just how extraordinary it truly is. The remarkable thing is that Earth was not always the calm blue world we know today. Long before waves rolled onto sandy shores or clouds drifted across the sky, our planet was something entirely different. A glowing sphere of molten rock surrounded by chaos. And somewhere between that violent beginning and the peaceful oceans we see today, lies a story that scientists are still trying to piece together. As we gently follow that story tonight, you may discover that the history of water is also the history of our own existence. Every ocean, every raindrop, perhaps even every glass of water you have ever held, carries a journey that began billions of years before the first mountain rose or the first living creature took its very first breath. So, find a comfortable place to rest, settle into the quiet, and let us begin our journey into one of the most fascinating mysteries in science. If you could travel far enough into space, leaving behind the moon and the neighboring planets, there is one world that would immediately stand out. It would not be the brightest, nor would it be the largest. Instead, it would catch your attention because of its color. From a great distance, Earth glows with gentle shades of blue and white. Vast oceans reflect sunlight into space, while drifting clouds slowly swirl above them like soft brushstrokes on an enormous canvas. To astronauts, it is often described as a peaceful world, a rare oasis surrounded by the darkness of space. More than 70% of Earth's surface is covered by water. The Pacific Ocean alone is larger than all the continents combined. Some places reach depths greater than 11 kilometers, so deep that Mount Everest could disappear beneath the surface with room to spare. Water shapes almost every landscape you can imagine. It carves valleys, feeds forests, fills glaciers, and carries nutrients across the globe. It rises into clouds, falls as rain, freezes into snow, and quietly begins the journey all over again. Because water is everywhere, it feels almost inseparable from the idea of Earth itself. Yet that comforting image hides an astonishing mystery. Scientists believe there was a time when none of these oceans existed. No waves, no rain, no rivers, no blue horizon stretching into the distance. Only fire. Imagine standing, not that anyone could have, on the surface of Earth more than 4.5 billion years ago. There would be no solid ground beneath your feet. Instead, the planet would resemble an endless ocean of glowing rock. Rivers of molten stone would flow in every direction. Giant cracks would open across the surface, releasing tremendous heat from deep inside the young planet. Above, the sky would not be blue. It would be thick with dust, glowing ash, and clouds of hot gases that blotted out the sun. Even if water somehow appeared in such a place, it would have faced an impossible challenge. Picture placing a tiny drop of water onto a red-hot frying pan. Before your eyes can follow it, the drop vanishes into steam. Now imagine that frying pan the size of an entire planet. That was the world Earth may once have been. It raises a simple but deeply puzzling question. How did a planet that should have destroyed every drop of water become the only known world in the solar system covered by vast, stable oceans? For generations, scientists have searched for the answer. Some believe Earth's water arrived from the cold outer reaches of the solar system, carried by icy visitors that repeatedly crashed into the young planet. Others think countless ancient asteroids slowly delivered water over millions of years, one collision after another, until the oceans gradually took shape. Another idea suggests something even more surprising, that Earth may have carried much of its water from the very beginning, hidden deep inside the rocks that formed the planet itself. And there is an even stranger possibility. Perhaps, even today, enormous amounts of water remain hidden beneath our feet, not as underground lakes or secret seas, but quietly locked inside minerals buried hundreds of kilometers below the surface. In other words, the oceans we see might represent only part of Earth's water story. Like many mysteries in science, this one has no single dramatic revelation waiting at the end. Instead, it resembles a giant puzzle whose pieces have been discovered one by one over decades of careful observation. Tiny crystals preserved inside ancient rocks, meteorites older than Earth itself, spacecraft chasing comets across billions of kilometers, diamonds rising from incredible depths inside our planet. Each has contributed a small clue. Taken alone, none of these clues tells the whole story. Together, they begin to reveal something extraordinary. And perhaps that is one of the quiet beauties of science. It rarely replaces one mystery with certainty. More often, it gently transforms a simple question into a richer understanding of how wonderfully complicated nature truly is. The story of Earth's oceans is exactly that kind of mystery. It stretches across almost the entire history of our planet. It begins before the continents existed, before the atmosphere became breathable, before the first cells floated through ancient seas. In many ways, the story of water is older than almost everything we usually think of as Earth. There is another reason this question matters. Water is not just something living things happen to use. It is the stage upon which life performs. Without liquid water, chemistry slows. Molecules struggle to meet. The countless tiny reactions that eventually produce the first living cells become far less likely to unfold. Water does not simply support life. It creates the gentle environment where life has the opportunity to begin. That realization changes the mystery in a subtle way. We are no longer asking only where Earth's oceans came from. We are asking how a once fiery world became gentle enough to cradle rivers, clouds, forests, coral reefs, whales, and eventually curious minds capable of wondering about their own beginnings. Perhaps the most remarkable thought of all is this. The water inside your body may be unimaginably old. Some of its molecules may once drift through the cloud of dust that surrounded the newborn sun. Some may have spent ages hidden deep inside Earth's interior. Others may have traveled through volcanoes, glaciers, oceans, clouds, and countless generations of living creatures before eventually becoming part of you, if only for a little while. Water is always moving, always changing, always continuing a journey that began long before human history. And to understand that journey, we must leave behind today's peaceful blue planet and travel back to a time when Earth looked almost nothing like home. Because before there could be oceans, there first had to be a world that seemed completely incapable of holding them. If Earth's oceans seem ordinary today, it is only because we have never seen the world that came before them. To understand where the water came from, we first have to imagine a planet that appeared almost incapable of holding any at all. The Earth we know today, with its blue skies, quiet forests, and endless coastlines, is only the latest chapter in a story that began with extraordinary violence. Let us travel back, not thousands or millions of years, but about 4.5 billion years into the past. At that time, there was no Earth. There was only a young sun, newly ignited, surrounded by an enormous swirling disk of gas, dust, and tiny rocky fragments. If you have ever watched flour slowly swirl through the air while baking bread, catching sunlight as it drifts and settles, you already have a gentle picture of what this ancient cloud may have resembled. Except this cloud stretched across billions of kilometers and contained enough material to build an entire family of planets. Within this vast disk, countless tiny grains began colliding. At first they were no larger than grains of sand, then pebbles, then boulders. Over countless collisions, gravity quietly gathered these fragments into larger and larger worlds. Nothing appeared overnight. Building a planet was less like assembling a machine and more like watching a snowball roll downhill, slowly collecting layer after layer until it became something enormous. One of those growing worlds would eventually become Earth. But its birth was anything but peaceful. Every collision released tremendous energy. Each impact was like striking a match, except on a scale almost impossible to imagine. As larger bodies crashed together, the young planet grew hotter and hotter. The accumulated heat came not only from these impacts, but also from radioactive elements deep inside the forming world, and from the immense pressure of gravity squeezing the planet inward. Eventually, the surface became so hot that much of it melted. Scientists often describe this stage as a magma ocean, but it helps to imagine something far more vivid than the name suggests. Picture an entire planet whose surface glowed orange and red, like the inside of a giant furnace. Instead of continents, there were immense seas of molten rock stretching far beyond any horizon. Mountains could not remain standing because the ground beneath them flowed like an unimaginably thick liquid. This fiery landscape lasted for millions of years. It was a world constantly reshaped by heat. Yet even during this seemingly hopeless time, Earth was already beginning to develop the ingredients that would eventually support oceans. Deep within the molten rock, various gases became trapped. As volcanoes erupted across the young planet, these gases slowly escaped into the sky. Instead of the breathable atmosphere we enjoy today, the early Earth was wrapped in a heavy blanket of steam, carbon dioxide, methane, sulfur-rich gases, and volcanic ash. If you have ever watched steam rise from a kettle on a cold morning, you have seen a tiny reminder of this ancient process. The difference, of course, is that Earth's young atmosphere contained enough steam to surround an entire planet. At first glance, this might sound encouraging. After all, steam is simply water in another form. But there was a problem. Having water in the atmosphere is not the same as having oceans on the ground. Imagine standing beside a kettle that never stops boiling. The room may fill with steam, but until the heat is turned down, that steam never settles into liquid water. Early Earth faced the same challenge. As long as the surface remained intensely hot, any rain that tried to fall would immediately return to vapor. Clouds might form, only to disappear again. Water could exist, but it could not yet find a lasting home. Whether Earth cooled quickly or slowly would make an enormous difference. If cooling happened fast enough, steam could eventually condense into rain. Those first rains may have fallen for thousands of years, gradually filling the lowest regions of the cooling planet. If cooling took much longer, however, the story would become far more complicated. And then came an event that changed everything once again. Not long after Earth began forming, another young world, roughly the size of Mars, is thought to have collided with our planet. Scientists believe this enormous impact eventually led to the formation of the Moon. It is difficult to imagine the scale of such a collision. This was not simply a large asteroid striking Earth. It was one planet crashing into another. The energy released was so immense that much of Earth's outer layers melted all over again. Vast quantities of rock were blasted into space before gradually coming together to form the Moon we see tonight. For our story, however, another question becomes even more important. What happened to the water? If Earth had already begun collecting water before this collision, much of it may have been heated, vaporized, or even lost to space. It is a little like carefully filling a bowl with water, only to have someone suddenly knock the bowl onto a blazing fire. Could any of it have survived? Or did Earth have to begin collecting water all over again afterward? This simple question quietly divides many scientific theories. It is not enough to ask where Earth's water came from. We must also ask when it arrived. Did it come before Earth's greatest catastrophe, or afterward? For many years, scientists believed the young Earth remained dry for a very long time after the moon-forming impact. Then something unexpectedly small began changing that picture. Hidden inside some of Earth's oldest rocks are tiny mineral crystals known as zircons. Most are no larger than grains of sand, and at first they appear entirely unremarkable. Yet these little crystals are among the oldest surviving objects ever found on our planet. They are like tiny time capsules. As they formed, they quietly recorded the conditions around them, preserving clues from an Earth that has otherwise disappeared beneath billions of years of geological change. When scientists carefully studied some of these ancient zircons, they found evidence suggesting that liquid water may already have existed surprisingly early, perhaps only a few 100 million years after Earth first formed. That discovery was astonishing. Instead of a planet remaining dry for an extended age, Earth may have cooled much faster than once believed. Oceans, or at least bodies of liquid water, could have appeared while much of the young solar system was still settling into place. The zircons do not tell us where the water came from. They cannot reveal whether it rose from Earth's interior or arrived aboard ancient visitors from space. But they tell us something equally important. Water was present remarkably early. Whatever its origin, it wasted little time becoming part of Earth's story. That realization transforms the mystery. Instead of asking how a dry world eventually became wet, scientists began asking how water managed to survive on a world that seemed determined to destroy it. Every proposed explanation must now pass the same demanding test. It must explain not only how water arrived, but how the very first drops endured a planet of molten rock, endless volcanoes, and colossal impacts. To continue searching for that answer, we must leave the young Earth behind and journey outward into the cold, dark reaches of the solar system. Because for many decades, scientists believed the oceans may have begun their journey among wandering worlds made of ice. As the young Earth slowly cooled beneath its thick blanket of steam, one question refused to fade away. If this restless planet struggled so much to keep water, perhaps the water had come from somewhere else. To explore that possibility, we must leave the warmth of the inner solar system and travel outward, beyond the rocky planets, into regions where sunlight grows faint and temperatures fall so low that water remains frozen for billions of years. It is here that we meet some of the oldest travelers in our cosmic neighborhood, comets. For generations, comets captured the human imagination. Long before anyone understood what they truly were, people watched glowing tails stretch across the night sky and wondered whether these mysterious visitors carried messages from the heavens. In a way, modern science asked a remarkably similar question. Could these wandering worlds have carried something far more valuable than a message? Could they have carried Earth's oceans? At first, the idea seemed wonderfully simple. If Earth formed close to the young sun, it would have been an extraordinarily hot place. Water ice could not survive there for long. But much farther away, beyond the region where giant planets were taking shape, the solar system was cold enough for enormous amounts of ice to remain safely frozen. Imagine a large freezer at the back of an old kitchen. Near the oven, ice melts almost immediately. But tucked away in the coldest corner, it can remain unchanged for a very long time. The early solar system may have worked in a similar way. Near the sun, rocky planets were born from heated materials. Farther away, frozen worlds quietly accumulated layer upon layer of ice. Many of those frozen bodies became comets. Although they often appear delicate from a distance, comets are surprisingly rugged objects. They are mixtures of ice, dust, rocky fragments, and ancient organic compounds, materials that have changed very little since the solar system itself was young. Some scientists like to think of them as cosmic time capsules. While planets continued evolving, melting, and reshaping themselves, many comets simply remained frozen, preserving a record of conditions that existed billions of years ago. If enough of these icy travelers struck the young Earth, the idea went, each collision could have delivered a little more water, not all at once, but little by little. Imagine filling a dry garden with snow, brought in one bucket at a time. Each trip seems insignificant. Yet after enough journeys, the ground slowly disappears beneath a blanket of white. Earth's oceans, according to this picture, may have formed in much the same way. For hundreds of millions of years, the young solar system was a crowded and chaotic place. Countless small worlds wandered through unstable orbits. Some crossed Earth's path, others collided with neighboring planets. Every impact released tremendous energy, but it also delivered fresh material from distant regions of space. Those impacts may have brought more than water. Many comets also contain simple carbon-based molecules, the kinds of ingredients that, under the right conditions, can participate in the chemistry of life. This led to an even more exciting possibility. Perhaps some of the same visitors that delivered water also helped prepare the stage upon which life would eventually emerge. It is a beautiful idea. Beautiful, but science has learned to be cautious around beautiful ideas. A theory is not accepted because it feels satisfying. It must agree with evidence. Fortunately, water carries an unexpected clue. At first glance, every drop of water appears identical, but hidden inside its molecules are tiny differences that act almost like a fingerprint. One version of hydrogen, the smallest and most common atom in the universe, is ever so slightly heavier than another. That small difference allows scientists to compare water from different places across the solar system. Instead of asking where water came from, they can ask whether two samples appear to belong to the same family. It is rather like comparing handwriting. Two letters may tell the same story, yet subtle details reveal whether they were written by the same person. Water leaves similar clues. When astronomers began measuring water from comets, the results were fascinating. Some comets appeared to carry water astonishingly similar to Earth's oceans. For a while, excitement grew. Perhaps the mystery had finally been solved. Then the picture became more complicated. As more comets were studied, researchers discovered that many carried water with noticeably different chemical fingerprints. Some were surprisingly close to Earth's oceans, others were quite different. It was as though the comets themselves belonged to several extended families rather than one large identical group. This presented an uncomfortable problem. If Earth's oceans had come almost entirely from comets, scientists expected the chemical fingerprints to match much more consistently. Instead, they found a surprising variety. One mission became especially important in this story. In 2014, the European spacecraft Rosetta arrived at Comet 67P after traveling through space for more than 10 years. Rather than simply flying past, Rosetta entered orbit around the comet, observing it in remarkable detail. For the first time, scientists could carefully study the water escaping from a comet as it approached the Sun. Many people expected Rosetta to provide the final confirmation that comets had supplied Earth's oceans. Instead, it raised new questions. The water measured from Comet 67P differed significantly from the water found in Earth's oceans. Far from ending the debate, Rosetta reminded scientists that the solar system is rarely simple. Yet another surprise soon followed. A different comet, known as Hartley 2, carried water much closer to Earth's own. Now the puzzle became even richer. Some comets seemed like excellent matches, others clearly did not. Rather than pointing toward one simple answer, nature appeared to be telling a more complicated story. Perhaps asking whether all comets delivered Earth's water was never quite the right question. Perhaps some did. Perhaps many never reached Earth at all. Or perhaps comets contributed only a modest share, while another source supplied most of the oceans. Computer simulations added another layer to the mystery. Many suggested that although comets certainly struck the young Earth, the total number of impacts may not have been large enough to account for all the water covering our planet today. That does not mean comets were unimportant. Far from it. Even a relatively small contribution could have added enormous amounts of water over millions of years. They may also have delivered valuable organic compounds that enriched Earth's early environment. But the growing evidence suggested something different from the original idea. Comets were probably not the entire story. Instead of being the sole architects of Earth's oceans, they may have been generous contributors to a much larger project. Science often advances in this quiet way. An appealing explanation is not discarded overnight. It simply becomes one piece of a larger picture. The mystery remains alive, but it grows more detailed. If the icy wanderers of the outer solar system could not fully explain Earth's oceans, scientists needed to look elsewhere. Their attention gradually shifted toward objects that appeared far less dramatic. No glowing tails, no brilliant displays across the night sky, only ancient dark stones quietly orbiting the sun. At first glance, they seemed unlikely candidates for creating oceans. Yet these humble rocky worlds would eventually provide some of the strongest clues in the entire search. By the time scientists began questioning whether comets alone could explain Earth's oceans, the search took an unexpected turn. Instead of looking toward brilliant visitors with glowing tails, researchers started paying closer attention to objects that rarely attract much attention at all. Asteroids. Unlike comets, asteroids seldom put on spectacular displays in the night sky. They do not grow long, luminous tails, nor do they announce their arrival with breathtaking celestial performances. Most appear as little more than dark rocks quietly circling the sun. At first glance, they seem almost ordinary, yet appearances can be wonderfully deceptive. Sometimes the quietest objects carry the greatest stories. Imagine walking through an old attic filled with dusty wooden boxes. Most look plain and unremarkable, but inside one forgotten box, you discover letters, photographs, and keepsakes that reveal the history of an entire family. Many scientists have come to think of certain asteroids in much the same way. They are not simply rocks drifting through space. Some are among the oldest surviving pieces of the early solar system, preserving materials that have remained remarkably unchanged since the planets themselves were still forming. If those ancient rocks contain water, they may also preserve clues about how Earth became a blue world. Not all asteroids are alike. Some are composed mostly of metals. Others consist largely of dry, rocky material. But one particular group attracted increasing attention because they appeared unusually rich in carbon and water-bearing minerals. These primitive bodies formed in regions cool enough for water to become incorporated into the minerals themselves long before Earth had finished growing. The scientific name for these ancient meteorites is carbonaceous chondrites, but you need not remember the term. It is enough to picture them as some of the oldest water-rich building blocks left over from the birth of the solar system. Unlike a block of ice, the water inside these rocks was not trapped as frozen pools waiting to melt. Instead, it became part of the minerals themselves, tucked quietly inside their crystal structures. It is a little like moisture hidden inside a piece of seasoned wood. The wood may look completely dry from the outside, yet careful heating reveals that water has been there all along. These ancient rocks carried their water in a surprisingly similar way. When fragments of such meteorites eventually reached Earth, scientists discovered something remarkable. The water they contained looked strikingly similar to the water found in Earth's oceans. Not identical in every detail, but remarkably close. Earlier, we learned that water carries something like a chemical fingerprint. That fingerprint allows researchers to compare water from different places across the solar system. When they examined these ancient meteorites, the fingerprints matched Earth's oceans far better than many of the comets that had once seemed like the leading candidates. It was an exciting discovery. Suddenly, a new possibility began taking shape. Perhaps Earth's oceans had not arrived through a handful of spectacular impacts from distant icy wanderers. Perhaps they had accumulated much more quietly. Imagine placing an empty bucket beneath a slow, steady drip. One drop seems insignificant. 10 drops change very little. Even 100 may barely cover the bottom. But if the dripping continues day after day, week after week, month after month, the bucket eventually fills. The process feels almost invisible while it is happening. Yet patience quietly accomplishes what dramatic moments cannot. Scientists began wondering whether Earth's oceans formed in much the same way. During the early history of the solar system, countless water-rich asteroids crossed Earth's orbit. Many collided with the growing planet. Each impact delivered only a modest amount of water compared with the vast oceans we see today. But there were not merely dozens of impacts. There may have been millions, spread across hundreds of millions of years. Those countless deliveries could gradually have supplied an astonishing quantity of water. The oceans, in this picture, were not created in a single dramatic event. They accumulated patiently, almost imperceptibly, one ancient rock at a time. There was another reason this idea became increasingly attractive. These primitive asteroids appear to contain more than water alone. Many also preserve simple carbon-based molecules, the kinds of ingredients that chemistry can gradually transform into more complex compounds under suitable conditions. It is important not to imagine tiny organisms hitching a ride through space. Scientists are not suggesting that life itself arrived inside these rocks. Rather, these ancient visitors may have carried some of the raw ingredients that life would later use, enriching Earth's surface long before the first living cells appeared. Picture preparing a garden. Before flowers bloom, the soil must first be supplied with water and nutrients. Neither guarantees that flowers will grow, but without them, the garden has little chance of flourishing. Water and simple organic molecules may have played a similar role on the young Earth. They helped prepare the environment. The rest of the story unfolded over immense stretches of time, as researchers continued studying meteorites collected from deserts, Antarctica, and other carefully preserved locations. Each new sample became another quiet messenger from the earliest solar system. These rocks had traveled through space for billions of years before finally reaching Earth. Some were older than our planet's oldest surviving surface rocks. In a sense, they allowed scientists to hold pieces of the ancient solar system in their hands. That is an extraordinary thought. Most of Earth's earliest history has been erased by erosion, volcanoes, earthquakes, and the constant recycling of our planet's crust. Meteorites, however, often escaped that long geological reshaping. They preserved memories that Earth itself could no longer remember. Piece by piece, these memories began fitting together. Computer simulations also strengthened the asteroid hypothesis. Models of the early solar system suggested that the giant planets, particularly Jupiter, may have subtly altered the paths of countless small bodies. Some water-rich asteroids that originally formed farther from the Sun were nudged inward, crossing the orbits of the young rocky planets. Earth happened to be waiting. Not every collision was gentle. Many released enormous amounts of energy. Yet over time, enough water may have survived these impacts to become part of the growing planet. Still, science rarely settles for a single explanation. Even as evidence supporting water-rich asteroids continued to grow stronger, researchers noticed that the asteroid story also had unanswered questions. Could these impacts alone supply every ocean? Did all of Earth's water arrive after the planet formed? Or had some water already been hidden inside the very materials that built Earth from the beginning? The more scientists learned, the more the mystery seemed to shift. Instead of choosing between competing ideas, evidence gradually hinted that several might be true at once. Perhaps asteroids delivered an important share of Earth's water, but perhaps they were adding to something that already existed. It is a subtle difference, yet an important one. Imagine moving into a new house. Some furniture comes with the building, other pieces arrive later in moving trucks. Years afterward, it becomes difficult to remember which items were always there and which were brought from elsewhere. Earth's water may tell a similar story. Some of it may have arrived from distant space, some may have been present from the very beginning. The challenge is discovering how much belonged to each chapter. To answer that question, scientists had to look away from the sky entirely. Their next clues would not come from wandering worlds or ancient meteorites. Instead, they would come from deep inside our own planet, hidden beneath layers of rock that no human has ever seen directly. There, surprisingly, they would begin to wonder whether Earth itself had been quietly carrying water since the day it was born. By now, the mystery has become far richer than it first appeared. Comets may have contributed. Water-rich asteroids may have delivered enormous amounts of water over millions of years. Together, they tell a compelling story. And yet, as often happens in science, every answer quietly opened another question. What if Earth did not begin completely dry? What if, hidden inside the very materials that built our planet, there was already enough water waiting to be released? It is an idea that sounds almost backwards. For many years, scientists imagined Earth as an empty vessel. Water had to arrive from somewhere else, like rain filling an empty pond. But gradually, another picture began to emerge. Perhaps Earth was never truly empty. Perhaps the young planet carried some of its own water from the very beginning, tucked away so deeply inside its building blocks that no one realized it was there. To understand this idea, let us imagine building a loaf of bread. If you only look at the finished loaf, it seems solid and dry on the outside. But every baker knows that water was mixed into the dough long before the bread entered the oven. During baking, much of that moisture escapes as warm steam, while some remains hidden inside the bread itself. The water did not arrive afterward. It was part of the recipe from the very beginning. Some scientists now think Earth may have formed in a surprisingly similar way. As the young solar system slowly assembled its planets, countless rocky fragments drifted together under the quiet pull of gravity. These fragments were not all identical. Some carried almost no water, others contained small but significant amounts of hydrogen and oxygen bound within their minerals. Individually, each fragment may have seemed insignificant, but Earth was built from an unimaginable number of them. Even if each tiny building block carried only a little water, together they could have supplied an enormous hidden reservoir. For decades, however, this remained little more than an intriguing possibility. There simply was not enough evidence. Then, little by little, new discoveries began changing the picture. Scientists started examining a rare group of ancient meteorites believed to resemble some of the original materials that formed Earth. These meteorites are known as enstatite chondrites. The name sounds technical, but what matters is not the label. What matters is that they appear to be close relatives of the rocky material from which our own planet was assembled. For a long time, researchers assumed these meteorites were almost completely dry. That assumption turned out to be incomplete. With increasingly sensitive instruments, scientists discovered that these ancient rocks contained more hydrogen than anyone expected. The hydrogen was not trapped inside pockets of ice. Instead, it had become part of the minerals themselves, quietly hidden within the rock. That may sound like a small detail. In reality, it changed an important piece of the story. If Earth's original building materials already contained hydrogen, capable of forming water, then our planet may have inherited part of its water naturally during its birth. It would mean that not every drop needed to arrive from distant asteroids or wandering comets. Some of it may have always belonged here. This idea gained even more attention through recent research, including studies suggesting that Earth's building materials may have been considerably richer in hydrogen than scientists once believed. The implications are profound. Instead of imagining Earth as a dry world patiently waiting for water to be delivered, we can begin to picture a young planet quietly carrying hidden reserves from its earliest days. Of course, carrying water inside rocks is not the same as having oceans. Those hidden ingredients still needed a way to reach the surface. Fortunately, Earth had a remarkable mechanism for doing exactly that: volcanoes. When we think of volcanoes, we usually imagine rivers of glowing lava spilling across the landscape. But lava is only part of the story. Volcanoes also release enormous quantities of gas. Today, when a volcano erupts, towering clouds rise into the atmosphere, carrying steam, carbon dioxide, sulfur compounds, and many other gases that had been trapped deep underground. The young Earth was far more volcanically active than the planet we know today. Imagine thousands upon thousands of volcanoes scattered across the surface, erupting again and again over immense stretches of time. Each eruption was not merely releasing molten rock, it was allowing Earth's interior to exhale. Some scientists describe this process as volcanic degassing, but the idea itself is beautifully simple. Picture opening a bottle of sparkling water. At first, tiny bubbles remain dissolved inside the liquid. The moment the pressure is released, those bubbles begin rising toward the surface. Something similar happened inside the young Earth. As molten rock slowly rose upward, pressure decreased, allowing trapped gases, including vast quantities of water vapor, to escape into the atmosphere. Little by little, the sky became richer in steam. At first, the surface remained too hot for liquid water to survive. But planets, like ovens, eventually cool. Over millions of years, Earth's temperature slowly fell. Then, at some point that scientists are still trying to understand in detail, something extraordinary happened. The atmosphere crossed an invisible threshold. Instead of remaining as steam, water began condensing into liquid. Clouds thickened. The first rains began to fall. Not for a single afternoon, not for a single season. Some researchers suggest that rainfall may have continued, on and off, for thousands of years as the young planet gradually cooled. Imagine standing beside a window during a gentle storm. Raindrops gather one by one before quietly sliding down the glass. Now, imagine that process continuing not for hours, but across centuries. Streams gradually filled low-lying basins. Basins became lakes. Lakes merged into vast expanding seas. The first oceans slowly took shape. Whether every detail unfolded exactly this way remains uncertain. Science continues refining the timeline as new evidence emerges. But the overall picture has become increasingly compelling. Earth did not necessarily receive all of its oceans from space, nor did it create them entirely by itself. Instead, both stories may be true. The planet may have inherited water within its original building materials, released additional water through relentless volcanic activity, and later received even more from asteroids and comets arriving from elsewhere in the solar system. Rather than competing explanations, these ideas begin fitting together like neighboring chapters in the same book. One chapter tells how Earth was built, another tells how its hidden water escaped, another describes visitors arriving from space with still more precious cargo. Piece by piece, the mystery becomes less about choosing a single winner and more about understanding how several remarkable processes work together across hundreds of millions of years. And yet, just when this picture seems nearly complete, another astonishing discovery awaits, because scientists have begun to suspect that even today, Earth may still be holding an enormous amount of water far below the oceans we know, a hidden reservoir unlike anything anyone once imagined. By this point in our journey, the story has become wonderfully unexpected. Some water may have arrived aboard ancient asteroids. Some may have traveled here inside wandering comets. Some may have been quietly woven into Earth's very foundations before the planet itself was fully formed. It feels like the mystery should finally be complete. And yet, perhaps the greatest surprise of all is not hidden somewhere far beyond Earth. It is hidden beneath your feet, not beneath the oceans, not beneath the continents, but deep inside the planet itself. For centuries, people imagined the interior of Earth in surprisingly simple ways. Beneath the thin crust where we live, they pictured an immense world of hot rock, gradually becoming hotter and denser as one moved toward the center. That picture, although broadly correct, left little room for one particular ingredient: water. After all, how could water possibly survive in a place where temperatures rise high enough to melt rock? It sounds almost impossible, but nature has a habit of surprising us, especially when we imagine that we already understand the rules. To appreciate this discovery, it helps to begin with a simple observation from everyday life. Imagine holding a dry kitchen sponge. At first glance, it appears empty, yet the moment you place it under a tap, it absorbs an astonishing amount of water. Later, even after the surface feels dry, you can squeeze it and watch water slowly emerge from inside. The sponge is not a container holding a tiny lake. Its structure simply provides countless microscopic spaces where water can remain hidden. Now imagine something even stranger. Suppose the water was not sitting inside tiny holes at all. Instead, imagine it became part of the sponge itself, woven into its structure so completely that you could not see it, yet it was still there. Oddly enough, this second picture is much closer to what scientists have discovered inside Earth. When researchers speak about water hidden deep within our planet, they are usually not describing underground oceans sloshing through giant caverns. That image belongs more comfortably in adventure stories than in geology. The real discovery is subtler. Far beneath the surface, under enormous pressure, certain minerals can incorporate water directly into their crystal structure. The water is not present as liquid pools. Instead, tiny building blocks of hydrogen and oxygen become part of the minerals themselves. The rock appears perfectly solid, yet hidden within it is water. This idea seemed almost unbelievable until scientists began uncovering compelling evidence. One mineral became especially important. It is called ringwoodite. The name itself is less important than what makes this mineral extraordinary. Ringwoodite forms only under immense pressure, in a region hundreds of kilometers beneath Earth's surface where conditions are unlike anything we experience in everyday life. For decades, researchers believed this mineral might be capable of storing significant amounts of water. The challenge was obvious. No one can simply travel hundreds of kilometers underground to collect samples. The deepest mines barely scratch the surface compared with the depths where ringwoodite exists. So how could anyone know? The answer arrived in an unexpectedly beautiful way. Sometimes, nature performs its own experiments. Occasionally, deep within Earth, extraordinary pressures create diamonds. As these diamonds slowly rise toward the surface through volcanic activity, they can trap tiny fragments of the surrounding minerals inside them, almost like insects preserved inside ancient amber. These tiny inclusions become messages from places humans cannot directly visit. In 2014, scientists examined one such tiny fragment trapped inside a diamond. It turned out to be ringwoodite. Even more astonishingly, careful analysis revealed that it contained water locked within its crystal structure. The discovery made headlines around the world. Many newspaper stories quickly announced that scientists had found an ocean beneath Earth's oceans. It was an unforgettable headline, but it was also a little misleading. There is no vast underground sea with waves rolling through hidden caverns. The truth is both quieter and, in many ways, even more remarkable. Imagine a thick wooden table. It may feel completely dry to the touch, yet every piece of wood contains moisture woven through its fibers. The water is not collected into puddles hidden inside the table. It is part of the material itself. Earth's deep rocks appear to behave in much the same way. The water is dispersed throughout enormous volumes of mineral, almost invisibly. Individually, each crystal contains only a small amount. Collectively, however, The total could be astonishing. Some estimates suggest that Earth's deep interior may contain water comparable to the amount found in the surface oceans, perhaps even more. Scientists continue debating the exact quantity, and the uncertainty remains significant. But the possibility alone transformed how researchers think about our planet. Earth may not simply have oceans. It may participate in an immense water cycle that extends far deeper than anyone once imagined. This hidden cycle unfolds so slowly that it is almost impossible to notice during a human lifetime. As tectonic plates drift across the planet, portions of the ocean floor gradually sink back into Earth's interior. Along with them travels water contained within rocks and sediments. Over millions of years, that material descends ever deeper. Some of the water becomes incorporated into minerals beneath the surface. Elsewhere, heat and pressure release part of that water again. Volcanoes then return some of it to the atmosphere as steam. Rain eventually falls. Rivers flow. The oceans are renewed. The journey begins again. It is less like a machine with moving parts than a planet quietly breathing. A slow inhale, a slower exhale, repeated across hundreds of millions of years. This realization changes the way we think about Earth's oceans. Instead of seeing them as a fixed collection of water resting on the surface, we begin to recognize them as part of a living planetary system. Water is constantly moving, not only through clouds, rivers, glaciers, and seas, but also through the rocks beneath entire continents. Some of the water you see today may once have traveled deep into Earth's interior before returning through volcanoes long after the dinosaurs disappeared. Other water may still be waiting below, beginning a journey that will not end for tens of millions of years. In that sense, the oceans are far older and far more dynamic than they first appear. They are not merely resting upon Earth. They are participating in an endless conversation between the planet's surface and its hidden interior. And perhaps this is where the mystery becomes most beautiful. The question was never simply, where did Earth's water come from? The deeper question is how a rocky planet learned to hold, recycle, protect, and renew that water across billions of years. Because having water once is remarkable. Keeping it long enough for forests to grow, continents to drift, and life to evolve, that is the true miracle. In the next part of our journey, all of these discoveries will begin fitting together. The asteroids, the comets, the hidden water inside Earth's building blocks, the deep mantle reservoirs. Rather than competing stories, they may all be chapters in a single, far richer history, one that transformed a world of fire into the only blue planet we know. By now, we have gathered quite a collection of clues. Some came from frozen travelers crossing the outer solar system. Others arrived inside ancient rocks that fell quietly to Earth. Still others emerged from tiny crystals hidden inside diamonds, carrying messages from places no human has ever visited. Each discovery has added another piece to the puzzle. And if there is one lesson science has learned over the past few decades, it is this. The history of Earth's water is almost certainly not the story of a single event. It is the story of many remarkable events working together over an unimaginably long time. In many ways, the search for Earth's oceans has become less like solving a mystery with one final answer, and more like restoring an old painting. Imagine discovering a faded masterpiece in the attic of an ancient house. At first, only scattered patches of color remain visible, a little blue here, a little green there. As each layer of dust is carefully removed, the picture becomes clearer, not because one dramatic discovery changes everything, but because many small discoveries gradually begin fitting together. Earth's history has revealed itself in much the same quiet way. Today, most planetary scientists no longer ask which single theory is correct. Instead, they ask how each process contributed to the remarkable planet we now call home. The story may have begun before Earth even existed. some of the tiny rocky fragments that gathered together to form our planet already contained hydrogen locked inside their minerals. As these countless building blocks slowly merged, Earth may have inherited part of its future water from the very beginning. Then came the long age of fire. The young planet melted. Its surface glowed like an endless sea of liquid stone. Deep inside, hidden water remained trapped within the hot interior. As volcanoes erupted across the planet, steam gradually escaped into the sky. Slowly, almost imperceptibly, Earth began releasing part of its hidden inheritance. Meanwhile, the solar system remained crowded with wandering debris. Water-rich asteroids repeatedly crossed Earth's orbit. Some collided with the growing planet, adding still more water. A smaller number of icy comets also joined the story, carrying frozen material from the cold outer regions of the solar system. No single delivery created the oceans. No single eruption filled the seas. Instead, countless processes overlapped, each contributing a little more to the world we know today. It is rather like preparing a favorite family soup. The vegetables alone cannot create the meal. Neither can the herbs, nor the water, nor the slow cooking. Each ingredient matters. Remove one, and the final result changes. Earth's oceans may have formed through a similarly patient recipe. That picture has become one of the greatest strengths of modern planetary science. It does not force nature into choosing only one explanation. Instead, it allows different discoveries to support one another. Yet, even after the oceans formed, another challenge remained: keeping them. This may sound like a surprisingly simple problem. If a planet has oceans, surely it simply continues having oceans. But our neighboring planets tell a very different story. Let us begin with Venus. Today, Venus is often called Earth's twin because the two planets are similar in size and composition. Yet standing on Venus would be impossible. Its surface is hot enough to melt lead. The atmosphere is extraordinarily dense, trapping heat so efficiently that temperatures remain scorching both day and night. Scientists believe Venus may once have possessed significant amounts of water. If so, that water eventually disappeared. Some escaped into space. Some was broken apart high in the atmosphere by sunlight, allowing lightweight hydrogen to drift away over immense stretches of time. The result is a world that may once have resembled Earth in certain ways, yet today is astonishingly dry. Mars tells another story. Billions of years ago, rivers carved valleys across its surface. Lakes filled enormous basins. Perhaps even shallow seas existed for long periods. We can still see their ancient shorelines preserved in the landscape. Yet Mars gradually lost much of its atmosphere. Without a thick blanket of air to help stabilize temperatures and maintain pressure, liquid water became increasingly difficult to keep on the surface. Today, much of Mars is cold, dusty, and quiet. Its ancient rivers survive only as memories carved into stone. Then there is Earth. Somehow, our planet followed a different path. Why? The answer appears to involve an extraordinary combination of fortunate circumstances. Earth is neither too close to the Sun nor too far away. Its gravity is strong enough to retain a substantial atmosphere. Its magnetic field helps shield the atmosphere from the steady stream of charged particles flowing outward from the Sun. Its interior remains active, driving plate tectonics and volcanic recycling that continually reshape both the surface and the atmosphere. Perhaps most importantly, Earth developed a long-lasting water cycle. Rain falls, rivers flow, oceans evaporate, clouds form, snow accumulates, ice melts, water sinks into rocks. Some travels deep into the planet before returning through volcanoes millions of years later. The cycle never truly stops. It simply changes pace. There is another remarkable puzzle that scientists continue discussing today. Early in Earth's history, the young sun shone less brightly than it does now. At first glance, that seems to create a contradiction. If the sun was fainter, Earth's oceans might have remained frozen, Yet, geological evidence tells us that liquid water existed surprisingly early. Researchers sometimes describe this as the faint young sun paradox. The name sounds intimidating, but the idea itself is wonderfully simple. Imagine lowering the heat beneath a pot of soup. Common sense suggests the soup should become colder, yet somehow it remains comfortably warm. Something else must be helping retain the heat. Scientists believe Earth's early atmosphere probably played that role. Greenhouse gases such as carbon dioxide and methane likely helped trap warmth, allowing liquid water to persist despite the younger sun's gentler light. Exactly how these effects balanced one another remains an active area of research, and that is an important reminder. Even after decades of study, Earth's water story is still being refined. Science is not a finished book. It is an ongoing conversation. New spacecraft continue visiting asteroids. Fresh meteorite samples arrive in laboratories. More sophisticated instruments reveal details that previous generations could never measure. Every few years, another piece of the puzzle quietly appears. Sometimes it strengthens an existing idea. Sometimes it challenges one. Either way, our understanding grows. Perhaps the most satisfying picture emerging today is not one of certainty, but of harmony. The competing theories that once seemed to argue with one another now resemble musicians in an orchestra. A violin alone cannot perform a symphony. Neither can a single drum. Only together do the individual voices create the full piece. Earth's oceans may have formed in much the same way. Inherited water, volcanic release, asteroid deliveries, occasional comet impacts. Billions of years of planetary recycling, each contributed its own quiet note. Together, they transformed a blazing world of molten rock into a planet covered by deep blue seas. And once those oceans finally settled beneath the sky, something even more extraordinary became possible: life. As our journey draws gently toward its end, it is worth pausing for a moment and looking back, not to retrace every step, but simply to appreciate how extraordinary the story has become. We began with a simple question: where did Earth's oceans come from? At first, it sounded like a question with a single answer waiting to be discovered, like finding the missing piece of a puzzle beneath the sofa. Instead, the deeper scientists looked, the more they realized that Earth's water is not the product of one remarkable event. It is the result of an extraordinary partnership between the universe and our planet, unfolding patiently across billions of years. Some water may have traveled here inside ancient asteroids. Some almost certainly arrived aboard icy comets wandering in from the cold outer reaches of the solar system. Some may have been quietly inherited from the rocky fragments that came together to build Earth itself. And even today, some continues its endless journey deep beneath our feet, hidden inside minerals, before eventually returning to the surface through volcanoes and the slow movements of our restless planet. It is a story with no true beginning or ending. Only movement, only change, only an endless cycle. If you were somehow able to follow a single water molecule across enough time, its journey would seem almost impossible to believe. It might begin inside a tiny grain of dust orbiting the newborn sun. Later, it could become part of the rock that helped form Earth. For millions of years, it might remain trapped deep underground before escaping through a volcano as invisible steam. It could drift high into the atmosphere, cool into rain, and fall into one of Earth's first oceans. Perhaps it would later freeze inside an ancient glacier. Perhaps it would flow through the roots of a fern when dinosaurs still wandered the continents. It might eventually pass through the body of a whale, evaporate once again into a cloud, fall as snow upon a distant mountain, melt into a river, and finally become the water in a glass, resting quietly on your table tonight. The molecule itself would never know the difference. It simply continues moving, patiently, faithfully, across ages so vast that human history occupies only the briefest instant. There is something deeply comforting about that thought. When we hold a glass of water, we are not holding something new, we are borrowing something unimaginably ancient. Some of the water around us today may be older than the continents themselves, older than the forests, older than the mountains, older even than the moon as we know it today. Water remembers, not because it stores memories in the way people do, but because it has quietly witnessed almost every chapter in Earth's history. Every ocean wave carries atoms that have traveled through worlds of fire and ice. Perhaps that is one reason standing beside the sea can feel strangely timeless. The water before you has been on a journey far longer than anyone can truly imagine, and this story does not belong only to Earth. Once scientists began understanding how water may have reached our own planet, they naturally began asking a larger question. Could the same story be unfolding elsewhere? Across our galaxy are hundreds of billions of stars. Around many of them orbit rocky planets. Some are larger than Earth, some are smaller, some circle dim red stars. Others travel around suns much like our own. Modern telescopes have revealed that planets are not rare exceptions. They appear to be one of the universe's favorite creations. If water can form naturally inside planetary building blocks, if asteroids routinely carry water-rich minerals, if comets wander through countless young planetary systems, then perhaps the ingredients that shaped Earth's oceans are not unique at all. Perhaps they are part of a much larger cosmic pattern. That possibility has transformed the search for life beyond Earth. Scientists are no longer asking only whether another planet resembles ours. They are asking whether it has experienced a similar history. Did it inherit water from its birth? Did wandering asteroids enrich its surface? Did volcanoes release hidden reservoirs into the atmosphere? Did rain eventually fall beneath an alien sky? These are difficult questions. For now, they remain beyond our ability to answer directly. Yet every new space mission brings us a little closer. Robotic explorers continue collecting samples from ancient asteroids. Powerful space telescopes study the atmospheres of distant worlds. Future missions may one day reveal signs of water clouds, rainfall, or oceans circling planets dozens or even hundreds of light years away. Perhaps somewhere, at this very moment, gentle waves are rolling onto a shoreline no human eye has ever seen. Perhaps rain is falling beneath another sky, or perhaps Earth's story is far rarer than we presently imagine. Either possibility fills the universe with wonder. One reminds us that life may flourish in countless places. The other reminds us how precious our own world truly is. Science does not yet know which answer is correct, and there is something quietly beautiful about that uncertainty. Even after centuries of careful observation, nature continues offering mysteries that invite curiosity rather than certainty. Perhaps that is one of science's greatest gifts. It teaches us that understanding is not a destination, it is a journey. Every discovery opens another question. Every answer reveals another horizon. The story of Earth's oceans is one chapter in that endless exploration, a chapter still being written. As our evening comes gently to a close, perhaps you will think differently the next time you hear rain tapping softly against a window, or watch sunlight shimmer across a quiet lake, or stand beside the endless rhythm of the sea. The water before you is not merely part of today's weather, it is part of a journey that began billions of years ago. It has traveled through volcanoes and glaciers, through drifting continents and ancient oceans, through clouds, rivers, forests, and countless living creatures. For a brief moment, it has become part of your own story. And one day, quietly and without hurry, it will continue its journey once again. There is something wonderfully reassuring in that endless cycle. Long after we are gone, the oceans will continue breathing with the tides. Clouds will continue gathering over distant mountains. Rain will continue falling onto valleys not yet formed. The same water will keep moving, just as it always has, patiently connecting the deep past with futures we cannot yet imagine. Thank you for joining me on this quiet journey through one of Earth's oldest mysteries. As you rest tonight, perhaps let your thoughts drift as gently as a cloud crossing a calm blue sky, knowing that every drop of water has its own remarkable story, and that, in a small way, your own story has become part of it. Until next time, may your evening be peaceful, your curiosity remain endless, and your rest be deep. Good night.